for. I would thank for the co-organizers also, and also for the Institute for having this space and the opportunity to present these works here. So what I'm going to talk, it's a bit about time crystal phases and some recent results that we got for applications in quantum technologies of these phases, specifically for sensing AC fields. So I'll try to give a miscellaneous of all of these works here that I've been working for, I would say, 5-6 years, and maybe focusing on this last one that is about the sensor applications of these phases of matter. So first of all, let me just thank for all of the collaborators of these works, from Leonardo Silva and Luis, that is also here in the school, from my institute in Niterói, Universidade Federal Fluminense, also from Universidade Federal de Santa Catarina, from the group of Eduardo Duzioni with Tiago Maciel, that is a postdoc, and also Antonio, that's now in the States, as I remember. Of course, from people from ICTP and CIS, Saro, Angelo, Marcello Donmonte, that was here last week, Federica and also Alessandro, that from CISA, and Jonathan Killing from United Kingdom, Ana Sampera, that's also participating in this work of sensors from Barcelona, and Marcos Quiró from the University of Paris. So just to give a brief outline how I intend to give this colloquium, I'll just try to go a bit from the historical side, perhaps, of this time crystal discussion, giving what is the definition of a time crystal phase, and then going for the most popular form of this phase, that is the discrete time crystals. They were also the first that were experimentally observed, and also showing that, I mean, it's possible to generate this phase in many different platforms. I'll just give an example that I find interesting, that we have work that is called the boundary time crystals in open systems. And I hope also that is going to be similar to many of the speakers about dissipative dynamics, such as Sebastian Diel was discussing these last days. And yeah, so later I'm going for the applications of this phase as sensors. So the main idea behind these phases is a very famous theory in condensed matter, that is our Landau symmetry breaking theory, which states that equilibrium spontaneous symmetry breaking phases, they occur when the ground state or some low temperature states of the system, they may fail to satisfy the underlying symmetries of our Hamiltonian. So we can have some Hamiltonians which has some symmetries, but if we go to the macroscopic limit and the systems, the subsystems can have some interactions, we can actually find some stable states that do not are not invariant to the Hamiltonian symmetries. And this is a very famous symmetry. It was very useful to classify and characterize many different phases of matter. Let me just put a few simple examples here, so we know that very well that we can have some ferromagnetic systems, such that even though the Hamiltonian or the interactions between the spins in your system can have some rotational symmetry, if you have some interactions in a macroscopic number of these spins, they can form some domains with preferred aligned directions. In such a way, we're breaking the rotational symmetry of underlying Hamiltonian. We can also think on some more crystal lattices or more general systems, where even though the atoms or your constituents can have some translational or rotational spatial symmetry, due to interactions, they can break this rotational symmetry and really forming different types of crystal organized lattices. And I mean, the list is very, very long, I would say. We can think of superconductors, charge density wave, and many, many others, till the appearance, I would say, of topological phases. And it's somehow intriguing that among all of these possibilities of breaking a symmetry of the Hamiltonian, it was only recently that, let me say, a bit more than 10 years ago, that Wilczek did the question, is it also possible to have a phase that breaks the time translation symmetry of our system spontaneously? And this is essentially the key question of a time crystal phase. So let me just put a bit the model or the discussion posed by Wilczek here. I'm not going to details, and it's going to be clear why I'm not going too much details in the model. But he proposed this very simple model where you could have particles in a one-dimensional chain, in a closed ring. And he considered the possibility that if these particles, they can have some attractive interactions among them, they could break the spatial translation symmetry, and therefore they could have some agglomerations in some very specific spatial positions. And given that you could have also some flux in this ring model, these quasi-particles or these lump particles, they could have some superconducting properties in a way that they would flow along the ring without resistance and therefore indefinitely in time in the macroscopic limit. So he proposed then that the ground state of this type of model here could have some long-range correlations, looking, for example, for the density at a spatial location and a specific time. But these long-range correlations is not only in the spatial time, but also in the time ordering, and therefore we have long-range spatial and time ordering, with these correlations having some very specific and periodic motion indefinitely in time. And therefore, we would have like a time crystal phase in this case here. Of course, that, I mean, right after the proposal by Wilczek of this very simple model, there was a lot of discussion about the real possibility to have this phase in this ring particle model, mainly by Lee, Bruno, and Volovic. And they had many different arguments, but let me say, I mean, among them, you could argue that you have then these lumps, they are rotating particles that at some point should radiate, and then you're not really in the ground state of your system, and these quasi-particles, they should at some point stop their motion, and you should lose the time or long time ordering in your ground state. And indeed, it was later shown that the ansatz used by Wilczek to compute these correlations here, it was not really the ground state, the real ground state of the system. It was an approximation of the ground state. Yeah. So this is a continuous symmetry? Yes. Yes, yes, essentially, yeah. What is Goldstone? So I don't know in details what would be the Goldstone bosons in this case here, but yes, but the idea is along this. But I don't know in details, I would say. Yeah. Okay, but I mean, I didn't go for details in this model because at the end of the day, there is this famous theorem here that was given by Watanabe and Oshikawa that actually proved that for a system with short-range interactions, it's impossible to generate this type of long-range time ordering in the expectation values of your system. So actually, they show that any system in thermal equilibrium cannot manifest this type of time crystalline behavior, at least for short-range ones, that because they use Lieb-Robson bound to prove their calculations. And apparently, I mean, even though the idea was very nice, it seems that at least in this framework or in this approach, it was not a good direction. But the main conclusion that the community took from this discussion here is not that it's not possible to generate this phase. It was just that we were looking at a different, at the wrong perspective. And perhaps the right perspective, it was not in equilibrium. It should be rather in non-equilibrium context to see for this phenomenology here. So, and then I would say when I say non-equilibrium context, it's either you do not look for the ground or thermal states, but you prepare your system in some excited state that would not be the eigenstate of your Hamiltonian, or you're really looking for some time-dependent driven dynamics and try to see the response to this driven dynamics of your Hamiltonian. So the first important steps were given actually looking for driven dynamics of this class of system that is called Floquet dynamics, where your Hamiltonian now it has some time dependence, but it has a discrete time translation symmetry where for multiples of specific period, the Hamiltonian is invariant to this time translation symmetry. Yes, it could be due to different external force acting in your system. But then, I mean, you see that since you have some external potential or some external force acting in your system, you should expect that your system heat up, and then at some point it should thermalize again, and you will not see this type of phase. But the point is that you can avoid this from different forms. I'm going to discuss a bit more about this. Yeah. So just to give, what should we expect then in this Floquet dynamics, the appearance or the support of a time crystal. And here, let me call this discrete time crystal because they're going to break a discrete time translation symmetry of the Hamiltonian. So in this case, then, there should be some macroscopic observables of my constituents and some initial states or a class of initial states, such that when you look for the expectation value of this macroscopic observable in the thermodynamic limit, you see some time dependent function here that first should not have the same symmetry as your Hamiltonian symmetry. So this time dependent function should break the discrete time translation symmetry. Moreover, it should be from a many-body phase and not just from a single particle dynamics. So even though we may have some perturbations or some imperfections in the Hamiltonian, this time-dependent function here should be stable and robust to the dynamics. And as usual, in spontaneous symmetry breaking, this type of phenomenology here should appear only if we are in the thermodynamic limit and not really for finite systems size. So this is perhaps the three main properties we should expect for the presence of this system, of these phases. And it was in 2016 that Dominique Bellabauer and Chetan Nayak proposed this nice model here that combines this Floquet dynamics with some many-body localization in order to support or to stabilize some time crystal phase. So the Hamiltonian is very simple. It has a time-dependent term, which is given by MBL Hamiltonian, and it has this time-dependent driving, which essentially do this X operator that's going to be a global kick on our system at every multiples of my period. So just to be more specific, the system is just a one-dimensional chain with spins, and the MBL Hamiltonian is just given by nearest neighbor interactions along specific directions for my spins. And on top of this, also, you have a lot of disorder external potentials on the spins. And the X operator, what it does is it does a global spin flip on all of my spins. So, I'm sorry, I didn't hear. I'm sorry? The number of parts? Okay. No, I mean, this is just stating that, I mean, at every multiple of the period, I just act with this X operator here. Yeah, I think that I'm going to put wave function here is going to be clearer also this part. Okay. So from one side, you have this MBL Hamiltonian here that we know that if you have just this time-independent dynamics from MBL case, you can generate correlations between the spins. And if the disorder is strong enough, it can fail to thermalize your spins. But then also we are adding this new term that is some time dependence kick to the spins. And then we want to see some different response from this time-dependent Hamiltonian. So yeah, so the Floquet dynamics or the wave functions evolves at stroboscopical time, so at a multiple of my full period, just given by this unitary Floquet operator acting in initial configuration of my spins. So perhaps here is going to be easier to interpret what's going to happen with this sum of this n to 0 to infinity. So we just have that in between the kicks, we act with the MBL Hamiltonian. And then at every multiple of the kick, we act with this big X flip operator. Just to be easy to understand what's going to happen in the dynamics, if we consider that this phi is equal to pi over 2, then expanding this type of kick operator is essentially just making the sigma X operator on all of my spins. That is just flipping globally all of them at the same time, okay? So then what you can observe is that if you initialize the system with a fixed global magnetization along the z direction, and you start the dynamics, you see that very fast the x and y magnetization of the spin, they thermalize. It means that it goes to an average expectation value equals 0, and locally it resembles like infinite temperature state. But if you look for the magnetization along the z direction that is given by the interaction in the MBL Hamiltonian, you see that it slowly decreases, but it has this persistent dynamics even for long times. So in between the kicks, you have this dephasing because of the MBL dynamics. And then at every multiple of the kick, you flip all of the spins, and instead of going everybody up, everybody goes down. But then you see that the system comes back to itself only at 2 times the period of your Hamiltonian. And therefore, even though the Hamiltonian has a discrete T symmetry, your dynamics, your observables, they are having a multiple of this symmetry of the Hamiltonian, and therefore breaking the translation symmetry. Yeah? The Z does not thermalize because the dynamics in between the kicks, it's given by this MBL Hamiltonian. And if this MBL Hamiltonian, I mean, it induces some interactions along the Z directions, but if you have enough disorder here in the external potentials, the thermalization is extremely slow in the system. And that's the mechanism, yeah. Yeah, I'm going to show, yeah. The order is exponentially slow in time. Yeah. Yes, exactly, yeah. Yes, exactly, yeah. I would say that, I mean, it's because the stabilization of the thermalization, it comes from this interaction here on the MBL. So it avoids a preferential direction for the thermalization. That in this case is roughly along the Z direction. But the other directions, they should not have any type of mechanisms to prevent this, yeah. No. What's flipping during the kick is the Z direction. So no, yeah, but the X comes from the Hamiltonian, but then when you make the exponential of the Hamiltonian, that is the exponential of X, is actually given by this string of sigma X Pauli operators. And each one of the sigma X, when you act along the Z direction, it makes the flip along the Z direction. Yeah, it was just, yeah, okay. Yeah, so I mean, it would be easier if I put, explicitly just the product here instead of making the, yeah, okay. Okay, so, and then, okay, we see this, this very slow thermalization along the Z direction with the period doubling, therefore breaking the symmetry of the Hamiltonian. But of course, that for finite systems, I mean, at some point, the system should thermalize. But what is interesting here is that if you look for the absolute value of the magnetization, just to see how long this period doubling magnetization can survive, you see that the thermalization is small, but of course, for finite systems, at some point, you have the dephasing, it acts strongly in your system, and it goes to 0, and you lose these periodic dynamics, or these ordered dynamics of the time crystal. But the lifetime of these oscillations here, the period double dynamics, is exponentially large with the number of spins in my system. So if I go then to the thermodynamic limit, or to the macroscopic limit, the lifetime should diverge, and I see this persistent indefinitely in time for the phase. Okay. And therefore, I really have the time crystal, or the main properties I mentioned at the beginning of the talk. So after the proposal of this simple model here, there were two experimental observations, one based on the entrapped ions, and the other one in defects in diamond. And the idea is essentially what Nyack model was saying. So they proposed these 3 steps now, Floquet dynamics, which has the main ingredients for the lack of thermalization and for subharmonic response. That is, they have some spin-spin interactions in order to couple the dynamics of all of my spins. They have some disorders among all of my spins in such a way that I can prevent thermalization for long times. And on top of this, they have this X operator that is the global spin rotation. Here is along the X direction, but it could be along in direction. It's just important to be along the direction of the spin interactions. And what they observe is essentially this type of phenomenology, that is the time crystal one. So here every color is for a different ion or a different defect in the diamond that can be treated as spin degrees of freedom. You see this period doubling, and if you make the Fourier transformation of the signal here, you see this subharmonic frequency stating that you have the period doubling oscillations of all of your spins. And let me say, I mean, I showed this type of, or the flip is perfect, but you could have some imperfections. It's not really 180 degrees of freedom, and you still see that the subharmonic frequency is robust as we expect for a many-body phase. It's not really a fine-tuned pointing of our Hamiltonian. So, I mean, this Floquet idea, actually, you can play a lot with this and show that many different models can support also this type of phases. And they do not need to rely only on disorder or many-body localization. You can also play with different mechanisms. So in this model here, for example, we studied how these long-range interactions can also support these phases or avoid thermalization. And specifically, we followed a similar idea as the Nyack paper or the Nyack model, where the Hamiltonian, it has, again, 2 terms. The first one is a time-independent model that generates correlations among the spins, and also avoid the thermalization. And a second term that is this global spin flips that occurs at multiples of my period. In this case here, we consider the Lipkin-Meshko-Click model that is an all-to-all interacting system. So now it's not really a one-dimensional chain. It's like a infinite connected chain. And on top of this, you can also have some external transverse field acting in these spins. So the idea here, it's a bit different, or the mechanism behind the non-thermalization, non-ergodicity of the spins is a bit different. Because you have in this model here 2 different phases. If the transverse field is stronger, you have just a paramagnetic phase with no order or correlation between your spins. But if J is larger than H, then your system can have ferromagnetic ordered states. And you have some degenerate states along this phase as well. But the important point is that it's not only the ground state that shows ferromagnetic ordering, but also the excited states in this model also can break the Z2 symmetry or have some ferromagnetic correlations in the states. So here I'm just showing the case for J larger than H, and for some eigenstates that are below some threshold, just showing the wave functions, how it depends on the magnetization along Z. And we see that we always have pairs of degenerate eigenstates for the Hamiltonian, which has either up spins, a ferromagnetic with up spins, or a ferromagnetic with down spins. And then the idea is that the kick now, what it does is that if we start in a ferromagnetic along a single direction, we act with the kick, and then we go for the other ground state of my Hamiltonian. And even if the kick is not perfect, does not make the connections between the 2 ground states exactly, we still have an extensive number of eigenstates that still have this ferromagnetic ordering. So then we can still avoid the full thermalization, and see the period doubling occurring in the system, even in this case. So here is just some simulations for 100 spins, for example, looking for the magnetization along the z direction, and we see this perfect period doubling dynamics here, and making some Fourier transformation on this dynamics here. We see that for a finite system, there are some beatings, so at some point, this period doubling should have some dephasing, and they are not really perfect period doubling dynamics. But as you go for the thermodynamic limit, these beatings, they converge to a single subharmonic frequency, and therefore recover the same idea of the time crystal operator. Yeah? Yes, but the doubling the period, it's breaking the symmetry, because the symmetry is that the Hamiltonian comes back to itself after a single period, right? Yeah, but usually you can think that you have two phases, but if you wait for a long enough time, there are some dephases between this going to one to the other. Let me say, to go to one ground state to the other ground state, and this phase just accumulating time, such that if you wait for a long enough time, you just lose this period doubling dynamics. So your system just thermalizes in the long time limit. So you need to have something more just displaying of different phases. Yeah. I keep the periodicity, yes. The period doubling, the periodicity, let me say, not a single period. Yes, but let me say, here is pi over 2, but it does not be a perfect flip. So you can think that this flip, it has not 180 degrees. You flip a bit wrong, and then if you accumulate this wrong in the flips, at some point, the average is going to be 0, right? And here, even if you don't have a perfect flip, you still have the subharmonic frequency there. So it's robust to these small imperfections, and the robustness comes from the interactions between the spins. Yeah, okay? So in this case, it's just the magnetization along the z direction here. Yes, yes, just yes, yes, yeah. In this case, yes. Yeah, but that's why, I mean, I was showing also that the real persistence of these phases here, it occurs only in the thermodynamic limit in order to discriminate between just single particle phenomena, okay? Okay, so I think that I'm running a bit out of time with what I planned, but let me just say that I showed for a spin system where you have period doubling, but it's also possible to generalize for n-tupling, let me say tripling or quadrupling, also more general discrete time crystals. And the idea, one way one can employ this type of idea is just looking for, instead of 2 degrees of freedom, you think that your subsystem can have any level degrees of freedom. And a simple way is just we can play with some clock algebra or clock variables among these n-level degrees of freedom. So we can define some tau operator that makes just the jump, the cyclic jump among all of the degrees of freedom of my subsystem, and some sigma operator that adds a phase to each one of my degree of freedom in such a way that I can interpret these different states here as some clock variables where the expectation value of sigma is just the tick of my clock operator here. So let me just be a bit more fast on this, but we essentially can use all of these tricks or these ideas of now we have a bunch of clock variables that could be either nearest neighbor interactions or these infinite range interactions just like in the LMG model. On top of this, we could also have some disorder in order to prevent thermalization and so on. And playing now with the kick that makes one tick of the clock, we see that we can break now higher orders symmetries of my Hamiltonian operator. Okay. So this Floquet dynamics, it was actually proven to be a very good or an excellent platform, let me say, for the support of Timecrystals. And at the time also we were thinking how general can be this phase, and specifically if it's also possible to break not a discrete time translation symmetry, but a continuous time translation symmetry in order to be a bit more general. And one possibility, it was looking for what we call these boundary Timecrystals, or is actually open system dynamics, where instead of looking for the whole degrees of freedom of my Hilbert space, I'm just interested in the dynamics of a boundary or of a part of my whole degrees of freedom, such that I can trace the information about what we call the bulk, and just look for the appearance of spontaneous symmetry breaking in a part of my system, but a macroscopic part nevertheless. So the idea of this boundary Timecrystal then is to focus on the boundary of the system. And let me say that here we are automatically out of the no-go theorem, so it's a good initial step to go towards it. And the idea comes essentially from surface critical phenomena, where you can have some phase that do not break the symmetry in the whole degrees of freedom, but just in a part of my full system. So just to be precise, Sebastian already presented a lot of this, also Cheng last week. But what we have is that we have the Hamiltonian that is composed by a boundary degrees of freedom, that's going to be the red spins here, or the red degrees of freedom, a bulk and some interactions between the bulk and the boundary. But since we are interested only at the boundary degrees of freedom, we know that the full dynamics is driven by the Schrödinger equation, but we can trace out all of the boundary bulk degrees of freedom and have some effective dynamics just for the boundary ones. And the effective dynamics is given by the density matrix evolution, which in its most general form is given by a CPTM map that preserves the physicality of the dynamics. So in the presence of Timecrystal in this context here, we should have then some macroscopic observable on my boundary degrees of freedom that shows some non-trivial time dependence that, again, is robust against imperfections, is stable, and persists only in the thermodynamic limit. So this is roughly the definition that we gave for boundary Timecrystal, but of course, to deal with the most general CPTM map, it's something very, very hard. And we go for some approximations in order to grasp some of this physics. We make some Lindblad or Markovian approximations for this boundary dynamics, where the CPTM map is given by what we know the Lindbladian operator, which has a coherent term that is given by the boundary Hamiltonian, and some Lindbladian operators that come from the interactions between the bulk degrees of freedom. So before going to some models that could show this boundary Timecrystal, it's nice to understand just from the spectral properties of the Lindbladian, what should we have there in order to stabilize this type of phases. So in the context of open dynamics, the density matrix it evolves with the Lindblad superoperator that can be roughly expanded with some generalized eigenvalues and some generalized projectors of the initial condition. But since now we have a Lindblad superoperator, we know that these eigenvalues, they can have not only an imaginary term, but they can also have some real part. And we can interpret these two terms here very easily because we see that the real part, it's always negative. So it's always going to give you the lifetime of the corresponding superoperators or the projectors, while the imaginary term is just giving a phase for these super projectors here. So in the general form, if you look for the spectral of these Lindbladians, you're going to see something like this, where you always have a zero eigenvalue with the real part equals zero. That is going to be the non-equilibrium steady state, is that if you wait for long enough times, your system is going to be driven towards this state here. And on top of this, you always have eigenvalues with the negative real part that gives some lifetime for the corresponding projectors, with or not some coherent oscillations given by the imaginary term. So in the presence of boundary Timecrystal, then, we should expect that there might be some eigenvalues which have imaginary parts such that they can induce some non-trivial oscillations in the expansion of my density matrix. But nevertheless, the real part in the thermodynamic limit, it goes to 0. So we should have some gapless excitations, because if this goes to 0, it means that the lifetime of the corresponding projectors, it should also diverge in the thermodynamic limit. Then these coherent oscillations here, they could persist indefinitely in time when you have a macroscopic system. So there is a very simple and interesting at the same time model that shows all of this phenomenology. It's a model, Chang also discussed a lot about similar models like this, that describes some cooperative emission of N2 level systems. And you have essentially two terms in the Lindbladian. The first one is just a magnetization along the SX direction. And the second one, it's a global flip of all of your spins, like an effective decay rate, given by a global de-excitation of my N spins. So this phase, or this model, was studied in the 70s and 80s. Let me say the steady state properties of this model was very well characterized. And we have essentially two different phases in this model. If the effective decay rate is the dominant part of my dynamics, then at a long time, all of my spins, they are going to be effectively pointing down, and we have finite magnetization for my steady state properties. But if we have that the transverse field is strong enough, I lose this finite magnetization, and they point roughly along the X direction. So these are the steady state properties, but here we are interested in the non-equilibrium dynamics of the system. And if we look then for the Lindblad spectral properties of this model, we see that these are the eigenvalues, the imaginary and the real part. We see that on top of the non-equilibrium steady state here, we can also have some eigenvalues with imaginary term, which means that we can have some coherent oscillations for these superoperators, projectors. But then if we make the finite size scaling, or see how these eigenvalues here converge when we go to the thermodynamic limit, we see that they do go to 0. I mean, this is just the real part as a function of 1 over n. We see that we have a lot of gapless excitations in the system. So we have this diverging lifetime for the projectors. But also, if we look for the imaginary part of these eigenvalues here, they come in these band structures, meaning that they can also generate some coherent dynamics for the corresponding eigenspace. So if we do really the dynamics given some initial state, let me say we initialize all of the spins along a given direction, along the x plus direction, we do see the time crystal appearing there, where for a finite system, the system shows some periodic oscillations, but essentially at the long time they thermalize, or they go for the non-equilibrium steady state, and you lose any time ordering. But as you increase the number of spins or go to the thermodynamic limit, you see that these oscillations, they have a larger lifetime and persistent with time then. Okay, so given that, I mean, the main idea was just to show that there are many different possibilities to generate these phases, either in closed system, Floquet dynamics, or in open system, continuous time translation. Let me also then move for these possible applications of this phase as sensors. So the main idea of these sensors, or the metrology with quantum systems, is that you have some external field, some AC field, that you want in the best possible way to measure it, or to infer the properties of this external field. And then for this, what you do, you get your quantum system, you make it to interact to this external field, and then when you put your spins to interact with external fields, the information about the external fields is going to be imprinted somehow in the dynamics of my internal degrees of freedom of my sensor. And then in a later time, I can measure then the spins and try to infer what was the external field of my AC fields. So essentially, we have that the full dynamics is given by the AC external field that I want to measure. either the amplitude or any other properties of my external field. And the internal dynamics, it can be a rather general one. So from one side, we know that entanglement is very helpful for these metrological sensors because it increases the sensibility of my spins to some external perturbation, and therefore it's easier to imprint this external information of in my spins. But on the other side, we also know that interacting non-equilibrium systems, they at some point can thermalize and they become noisy, and we lose all of the information about these external fields. So the balance between these two properties here is not easy for sensors. Usually people use dynamical decoupling. That's when you put your sensor to very fast frequency pulses, and in this way you essentially mitigate the interactions between the spin degrees of freedom and allowing for larger, longer coherence time. But of course, at the same time, you do not really exploit all of the quantum correlations or the quantum properties to improve your sensor performance. So let me say there are actually many different approaches. They're either based on these fast pulses or using these fast pulses with some highly entangled states in order to generate some pre-thermal dynamics. And let me say that this was perhaps one of the experiential work of our work that was given by Mishra and Bayat, where instead of looking for these dynamical decouplings or fast pulses, they tried to really look for some integrable Ising chains and exploring all of the many body correlations, specifically close to the phase transitions of the model. So as it is clear, I mean, the idea then is using these discrete time crystals as our sensors, and we have chosen specifically the time crystals given by NIAC that uses MBL correlations on top of these global kicks on my spins. So just to be more formal, how we approach the performance of my sensor, the steps are very simple. So we initialize our spins in some specific states. Then we put these to interact with this external signal. Then the state is going to have some time dependence, but also it's going to depend on this amplitude of my external field. And then in a later time, I make the measurements of my spins with some POVM measurements and try to infer what's the information about the AC field. Yeah. Yes, yes. Yeah. Yes, yes, exactly, yeah. So the full dynamics is given by these, right? So you have the discrete time crystal dynamics here with MBL and the kicks, and on top of this, you also have this external AC field acting during the dynamics. Okay. I'm sorry? In principle, they are uncorrelated, yes. They can be anything, yeah. But the performance of the sensor is going to depend on how you tune these two things. Yeah. Yeah, but here, for example, you can think that you want to measure the amplitude of the AC field. Then, I mean, it does not really depend on the frequency of these two things. Yeah. Yeah. Let me say it this way, yeah. Okay, so the protocol is this way. It's very simple, these 3 steps. And of course, it depends a lot on what is the measurement that you do in your spins. But there is this very interesting theorem, this is the Kramer-Rao theorem, that says that if you look for the best measurement possible, or if you maximize over all of the POVM measurement of your spins, the best uncertainty or the least uncertainty in order to determine this external field, it's bounded by 1 of the square root of this function here, that is simply the Fisher information of my system. So the Fisher information is given by this equation here, and it sees somehow the susceptibility of my state to small variations of my external field. So this is a very simple form to approach the best possible performance of my sensor without really caring about how is the protocol for measurement, what's the type of observer, and so on. So maybe this will be in a later moment to analyze really in a practical sense, but at least from a theoretical point of view, it's interesting to look from the Cramer-Rao bound. So just to have some intuition what to expect here, if we go to the simplest case where phi is equal pi, it means that we make the perfect kick or the perfect flip over my spins. And let me just disconsider that we have any imperfection in the MBL dynamics. There is no transverse field. So it's a purely classical dynamics, let me say. If you have all of your spins up, after one kick, it's just all of the spins down. So there is nothing more than this. And then if we have this AC field, we see that in order to imprint in the best form this AC field on the dynamics of my internal spins in the sensor, we should make the dynamics completely coherent with the external AC field. So let me say, if the AC is positive, all of my spins, they acquire the phase in the positive form. But then after the AC becomes negative, I make the full kick on my spins, and I still keep in phase with the external field in such a way that I don't have any dephasing or off-resonant effect because of some mismatching of their frequencies. So in some sense, in this very simple case here, we see that when we match then in period doubling resonance, we can get the best response or the best performance for my sensor. But now, of course, I mean, going for the general case, that is the most interesting, where you have not a classical dynamics, we can also have quantum correlations in the system. We observe this type of performance here. So just looking first for the period doubling dynamics of my spins. And here I'm just looking first for the linear response. That is the easiest case, I would say. We see what I have already told, right? We have this period doubling dynamics that has some lifetime that is exponentially with the number of spins. And at some point, I lose the time crystal behavior and the system fully thermalized. But then if you look for the Fisher information, you see that is directly related to the persistence of this period doubling dynamics. You see that the Fisher formation, it has an optimal growth up to a certain time, and this time is essentially the lifetime of my period doubling resonance. So we have this exponentially large in the system size for the performance of my Fisher formation. And then if we look for a full tomography or a full scanning for the Fisher formation over different mismatchings of my frequency, we see a few interesting properties as well. So the first one, we see that the best response it's given when I am close as possible to the period doubling resonance. And this came also from the intuition in the classical case. We see that this response here, it's rather than noisy, is actually in a very structured form. And this comes because we have a many-body phase that is not really all of the spins have its independent dynamics. It's really in a collective form. And perhaps most importantly, we see that this peak or the maximum perform of my sensor, the Fisher formation has a growth that depends on a beta, and beta here, it's larger than 2. And let me just say that when beta is equal to, we have a quadratic growth of the Fisher formation, is the maximum that one can do with just classical correlations. Everything that is beyond b equal to, it means that we are now exploiting the quantum correlations in a coherent form for my sensor. Just to contrast with the ergodic part of my sensor to see the difference, if we have some bigger imperfections in the Kiki or any other terms in the Hamiltonian, we would have rather these fast thermalizations of my period doubling resonance. There is no time crystal here, for example. And if you try to make this scanning of the Fisher information for different frequency, we see this rather response signal. And important, it's always below the t squared growth. It means that it's always below the classical limit for a sensor as well. So going then for beyond the linear response, imagine that we don't want to measure just infinitesimal amplitude fields, but also we want to measure finite fields. We see that these finite fields, they are going to be dominant after some characteristic time scale that's inversely proportional to the AC field, is when the information of the AC field is strongly settled in the dynamics of my spin. And after this time, actually, I mean, it does not really depend on what's the sensor nature or the correlation of the sensor. The behavior is roughly the same. So if you see the feature information, what you see is that you lose the quantum correlations or you lose the quantum improvements for the sensor and actually recover the quadratic classical limit for the sensor performance. So to summarize, perhaps in a single slide, what we saw is that looking for the uncertainty to measure this external field with these Floquet sensors, we can have different behaviors. If we have just an ergodic system or non-interacting system, we can have some decay of this uncertainty, some good performance for the sensor, but it's just for a few periods, so it's just order 1 in time. And after this, the system thermalizes, become noisy, and the uncertainty is just always smaller than the classical limit. But on the other side, if you try to use the discrete time crystal phase that has this long-range time ordering, we can keep this good precision or good performance for the sensor for exponentially long times with the number of spins. And importantly, it's always beating the classical limit. So in some sense, it seems to us that this could be promising, so offering some good advantage for metrology and sensing task. So essentially, we see this low heating that can overcome classical limit, and it, let me say, is also robust against imperfections in my spin interactions. So to conclude then, I mean, what I try to discuss here, it's what is essentially this type of phase. I mean, how they can appear in different platforms, ranging from discrete closed system, open, continuous one, and also, I mean, today there are many other types or different forms to stabilize this phase. But it's always interesting to think on different candidates also that can be based on different mechanisms as well. And I also try to show a bit some steps for quantum application of this phase, specifically in metrology, where we see that we can improve the performance using the correlations and the long time ordering of this phase. But we would also be interesting to see this other type of time crystals if they can have better performance as well for this sensing task. So just before finish, let me just make a small advertisement. I mean, if someone is interested on this type of topics here, just look for me. I'll be very happy to discuss as well, because we also have some open postdoc positions in collaboration with Serra Pilheira Institute. And given that, I thank for your attention. Yeah.
Question? Dominic? Two quick questions. So, which is the nature of the quantum correlations in the discrete and crystal that helps you to this kind of quantum?
Yeah, the nature of the quantum correlations come from dephasing between the spins. So you really don't have really current of spins, let me say, of energy, like Saro maybe mentioned in the seminar. But the spins, they still can have some dephasing in their dynamics, and this dephase is what creates the correlations between them and the spread of the entanglement between the spins. So in this case, though, the correlations or the entanglement is not ballistic, neither sub-ballistic, it's just logarithmic in time. Yes, exactly, yeah. That's the mechanism, yeah.
And the second question, it seems that the output is very limited to both fields in your design, right? Because there's this time scale for H that will always be a limited factor over time as well. If folks have any suggestion of improving that in the future?
So,
because there are other sensing protocols in that
so I would say, I'll not say if this is such a big limitation, because you have this characteristic time here that's inversely proportional to 1 over AC. But till you get to this characteristic time here, you can have some improvement due to the quantum correlation of the system. Okay, so I mean, perhaps the question is how can we prove this beta here? It's something that I didn't say, but beta is not 2, I mean, it's not 1, it's 1.1. It's not really much larger than the classical limit. But if you can improve this beta, perhaps using some phase transitions in the phase or something like this, then when you are close to the characteristic time, you have out of the very good precision or a very small uncertainty for for your parameter that you want to determine. Yeah. So yeah, this is one point, but I would not say that this is such a big issue, at least from a rough view, I would say.
I don't know if I understood this correctly, but you showed that graph with the function f versus frequency, and it seemed like
I think it's this one. Yeah.
So it seemed like it's getting narrower as time goes. Is that correct?
Yes, that's correct. Yeah.
That means then that you have to. I mean, it's not quite correct to say that you get an improvement unless you are very close to the.
Depends, yeah, I would say it depends on the time that you want to make the protocol. In some sense, depends on this characteristic time as well, 1 over the amplitude of the field that you want to measure. Because yes, if you want to measure really a tiny, tiny field and you want to keep this improved performance for long times, you need really to be at the period doubling resonance exactly, so you cannot really miss these things. Yeah, so this could be for sure some potential issue for the practical sense of this protocol as well. Yeah.
Kind of know the frequency, you could assume omega s or something like that.
Yeah, perhaps there are ways to overcome this. Yeah, but this is an important point in any case. Yeah.
Maybe you mentioned this, but does the coherence play any role in this?
Yes, I mean the coherence in the sense of not really the coherence, I would say more the phasing in the sense of the stability of the time crystal phase. Because if you lose the stability of the time crystal phase, then you are not in resonance anymore with the external field. And then you're not really capturing the best possible way this external field anymore. So, no, here is, we're just considering, here we're just considering, let me say, the first step in the simplest case model, that is just a Hamiltonian model with no decoherence to the external band, So let me say, that's why I think that there are many interesting perspectives, I would say. Not only are they different, but also in a practical way, what are the effects of some environment and so on, yeah. Yeah.
I remember in Floquet theory, usually when we look for a Floquet Hamiltonian when it's time independent, and one could write, for instance, a series, a high frequency expansion or a low frequency expansion. And I'm just wondering whether you can extract information about this time crystals using normally time independent Floquet Hamiltonian.
Yeah, I know. I mean, there is some Magnus expansion that you can do for the Floquet, such that instead of have some time independence, you have a time independent, but this time independent Hamiltonian can be rather nasty, right? Yeah. So I don't know of any works that try to make this approach in the time crystal phase, but yes, yeah. But even for simple Floquet models, it's not so simple also to expand in a good form this Magnus. Yeah, I would not know, but if there is something along this, it would make a lot of more easy dynamics. You know? Okay. Okay, yeah. Yeah, but that's a very good point.
Well, actually, you get the degeneracy. You get two Floquet eigenvalues which are shifted by pi over 2, which are degenerate.
No. Yeah. I mean, so I mean, for example, in this model here, we studied with more details about this phase transition. I'm not going back. So the clock model, let me say, but also in the LMG, we studied to see what's the characteristics of this phase transition. But it's essentially when you lose really the period doubling resonance, and you have some different subharmonic frequencies. So you can characterize the phase transition by this order parameter. But we saw that it was always in first order phase transition. It's not like a second order with some diversion or critical exponents. And I think that also for the LMG with Nayaka, it's something similar to this. It's like first order, if I remember well. Yeah, something like this. Yeah. I don't know, but here at least we are in open system dynamics. Yeah, so we are. So I know just the one paper that tried to break the continuous time translation symmetry in closed system. It's by Sasha, and he looks for some eigenstate. Yeah, it's similar, let me say, to the Wilczek paper, where you see these superconducting lumps. But not really looking for the ground state, rather some highly excited subsector of the Hamiltonian. But I don't remember of any discussion of Wagner arguments or anything like this, yeah. But this is the only paper that I know for continuous breaking of enclosed system, right? Yeah.
Okay. Thank you very much, Fernando.
Okay, thank you.